Loud. All right. Want to check in real quick. Everything okay with like Canvas? The quizzes are making sense. Stuff. Seeing the recordings, everything makes sense. It's just I'm just doing a YouTube link instead of uploading it to like YouTube Studio or Canvas Studio or anything. All right. Yeah, it's nuts. We're already in week 3. And today we're gonna dig deeper into consolidation. So isn't it mess up? We're just focusing on consolidation. We got through everything that we needed to for the soil stresses. So just as a recap, consolidation occurs in what type of soil mainly? What type of soil do we care about consolidation? Clay. Yeah. So for drilling down and it's just 200 feet of sand beneath us, we're like, we don't have to worry about consolidation at all. We don't have to do any of those testing. If we have layers of clay or organic or silt or anything that has a low permeability coefficient, then that's when we can get into the consideration of consolidation. And the whole analogy I was using last time about consolidation is the whole water balloon thing. And I think that's a pretty like accurate representation. Like imagine having a water balloon filled and then just poking like 2 little holes in it. When you squeeze the water balloon, it's going to take a long time for the volume to change and for that balloon to deflate. And that's essentially what's happening with the clay. When we squeeze the clay, the water or the pore water pressure does not dissipate automatically, allowing it to essentially trap and not change volume. And then over time, it will release, and then we'll have deformation or volume change of that. So where we are, or just as another update, week 3, so lecture 4 already. So we're sticking in consolidation for this class and the next few classes. I'm going to go through the laboratory setup, or sorry, the like how to actually like measure kind of the basics of the laboratory experiment for the consolidation test. And then in the next few weeks, we'll be getting more into actual calculations of consolidation settlement in the field, which is what you care about. That's going to be the thing that is a major design constraint. So we'll have another quiz this week, just as a little check-in quiz, and then I will post the first homework on Thursday. And so on Thursday, we'll go into a little bit more detail about like what to expect for that. You'll have at least a week, so I'll probably make that due on Sunday of the following week. And I need to make sure, I don't remember how much I normally give for that. But just want to put on your radar, you'll have that assignment coming up soon. Any questions on schedule or issues so far? Cool. All right. So same resources as before, consolidation settlement. So what we're going to be covering today is consolidation testing in the laboratory, difference between normal and over consolidated, and then estimations of consolidation settlement in the field. So we kind of already touched on this last class over normally consolidated, as well as consolidation testing in the laboratory. But now we're going to look at real data and then start introducing some of the estimations of consolidation settlement. And then the big thing along with this too, eventually what we'll get to is the time. That's a huge thing because like the water balloon, again, like depending on how much you press on it, it could take just 5 minutes, it could take an hour. And from a construction standpoint, that could translate to, it could take 2 years or it could take 1,000 years. And one of them is probably more crucial, right? If we're going to see settlement of this building in 1,000 years, maybe we don't care as much as if it is going to settle in the next 5 years. So the time aspect is also important in consolidation. Okay, so remember a little overview of what the consolidation test is comprised of. So remember, this is samples taken from the like in situ layer. Does anyone remember what is the name of the testing apparatus that we take the samples using? It's not the standard penetration test. What do we use? No, that's yeah, Shelby tube. So a cone penetration test does not retrieve any samples. So that's a big thing to remember. Cone penetration test is just a sensor pushed into the ground, so we don't retrieve any samples. The standard penetration test is a split spoon, so like a hollow tube that you can split open, and it's hammered into the ground. And so that hammering, why might that not be beneficial for a consolidation test? Yeah, you're going to completely you're going to crush the fabric in itself, right? So you're going to take that water balloon and then just pop a bunch of holes in it, so where we need the natural depositional fabric of the clay to remain intact. So although it's not perfect, the Shelby tube is a better alternative. It's a thin-walled tube. It's a little bit larger diameter. I think it's like 4 inches. Shoot, I was going to bring one. I'm sorry. They're in the lab. I'll bring it next time, I promise. And then it's kind of sharp. It's like beveled on one side. And what happens is instead we drill to the depth of the clay, and then we lower the Shelby tube, and then we push it in. We don't hammer it. So you just use the drill rod, the ram in the back, the hydraulic ram, to slowly push it in. And then we wait like 30 minutes for the pore water pressure to balance out. And then when we pull it up, it will be stuck inside of it. And then what is normally done is extruded out like a push pot, like the old school push pots. We don't drill it, we don't split it open. We extrude it out and then cut it off very carefully. So once we take that trimmed soil specimen, so yeah, Shelby tube, sample, extruded, and then we start here. The soil specimen is placed inside a metal ring with porous stones, and it looks like that little schematic right there. And then a load is applied over time, and then another load is applied over time, and it's this incremental load. And then from that change in the dial gauge, so what we're doing is essentially measuring the change in height over time of the sample. We can calculate the change in void ratio, and then we know the amount of load that we put on each step. So then from that, we can actually get the void ratio versus the pressure, which is the thing that we plot in the consolidation curve. Now, the last step, though, is taking the sample and then measuring the dry unit weight of that sample. And so this is performed at the very last step after multiple 24-hour increments. And so what you'll see through this test and why it can be kind of sketchy, it's not sketchy, well, yeah, it is sketchy, can be kind of like scary with this test is you can be collecting all of this data. So over like a week's worth of data, a week's worth of engineering time and laboratory fees. And then this last step of taking the sample, oven drying it, that data is required to have all of that data make sense. So the data, the very last step, is required to make all the previous data make sense. So you could accidentally screw it up at the very end, and then all of that data that you just spent a week worth collecting is essentially useless. So that's one of the things you have to consider, which is why a lot of labs are like, we'll put a little price on these consolidation tests just for the time required on it. So if we talk about like what is happening during the consolidation, if we were to plot the time on the x-axis versus a theoretical deformation, what we would see is that the deformation or the compression of the soil sample is occurring in this shape here, this like little S or three-phase shape, where we have an initial stage, a second stage, and then a third stage. So the initial stage, or the stage 1 shown in yellow, this is exactly what we call it, initial compression. Now, this isn't true consolidation. This is caused by preloading. So the water moving around a little bit, or the soil slowly settling back into its spot as a result of just being a disturbed sample. Now, the second part, stage 2, the blue part, this is what we call primary consolidation, and this is the one that we care about. Primary consolidation is where the change in volume is a result of the excess pore water pressure dissipating. So that's where the balloon is actually changing volume from the water leaving. And then stage 3 is the secondary compression. Sorry, secondary consolidation. Now, secondary consolidation occurs after complete dissipation of the excess pore water pressure. So this means the pore water pressure in the sample itself is now equal to the surrounding conditions. There's no like excess, there's no change in it. So any of the deformation occurring here is because of what we call just like plastic readjustment. Of soil fabric. So this would be actually like if you think of like a sponge situation, like when all the water is squeezed out of the sponge, and now when you push on it, what you're doing is actually just like tearing the sponge fabric. So from a soils perspective, you're readjusting the soil fabric. And now the reason why we talk about these three stages is because it's important when you're reading or performing consolidation test data to make sure that we are in a stress and a time frame that reads this primary consolidation. So this is the one that we care about the most. This is primary consolidation. That's what we're going to show all these equations coming up in this end of this lecture, next lecture, that are only to estimate primary consolidation. Which means if we are using laboratory data to estimate primary consolidation, then we need to make sure that that laboratory data is actually capturing the primary consolidation. So in some of the data, maybe I'll try to find some reports for consolidation tests with bad data, just how gnarly it looks. But it's important when you're performing the experiment that our stresses that are the loads that we're adding are within a range where we would anticipate that primary consolidation. Now, there is an area where secondary consolidation is important, and we'll come into this later after we talk about primary consolidation. Secondary consolidation still is a pretty big issue here in Florida for a specific type of soil like that we have here in Florida. Can anyone guess what type? Think about secondary consolidation is like the crushing of the fabric itself. What might be a soil type that experiences a high amount of secondary consolidation? Think about Florida. What'd you say? Lime rock? Not really. It's more elastic, but it's a. Uh-oh. Well, that's sweet. Sorry. Dude, what is up with UNF stuff? They didn't like that I made fun of football. Computer just restarted. No, so sick. Organic material as it's restarting. So that's one of the areas that we would experience a lot of secondary consolidation because what's happening is the plant matter and stuff gets all the water squeezed out of it, but then it's what's left is plant matter that's still super soft material, so that can squeeze too. So there is not as like in some areas where you have just only clay, they might only care about primary consolidation. But if you're working in Florida, especially in an organic rich clay or sand deposit, then it's not too uncommon to still have this additional testing to perform secondary consolidation. And the big thing, the way that we do that is by testing for time. So we just extend the test a little bit longer. And I'll upload the ASTM so you can reference that too for it. Oh my goodness. Give me a sec. Sick. Power saving mode. It's great. Oh. I think the computer is expecting to have a hurricane day or something. It's confused. Like we normally have a day off this week. Come on. Good thing is, I think it's still recording, so there's just going to be a super long commercial break during this time. Can I pause recording? All right, and we're back for the next 5 minutes, probably. Okay, so moral of the story for this slide. Primary consolidation, keep that in mind, that there might be more than just the primary consolidation. But the primary consolidation is the biggest chunk, and that's the one that's easiest to define from a mechanics standpoint. The initial one is like more elastic settlement. The secondary consolidation we'll talk about at the end, like in a few weeks. But the primary consolidation is the big thing that we are using this test to find. So let's talk about how we find it using the laboratory setup. So at the end of the day, what we are looking to do is produce, I showed this before, is we have the void ratio on the y-axis versus the load from the experiment, which is often shown in pressure. And this is in a log scale. So it's a semi-log plot, just like we did for the grain size distribution and everything. And so the void ratio, we know that the smaller the void ratio is, the more compact or dense the sample is. So as we are increasing the load going from left to right, we should expect to see the void ratio decrease. And what we see is as we populate the data like this, it kind of has a turn, like a curve that looks like that. And so what we care about with this is the two slopes of these lines, the two generalized slopes of these lines. So what we're trying to find from this, or the thing that populates this, is a void ratio for a corresponding stress. And then another void ratio for that same corresponding pressure or stress. So that's essentially what we're doing. So E1, E2, those are all the void ratios as we go along the experiment. So keeping that in mind, what we are looking for is, this is the pressure plot, or that's what it's often called. So what we first need to do is we first need to calculate the height of the solids in the soil specimen. And we use this equation. And the reason why we care about the height of the solid portion is because since this is a one-dimensional test, the three-dimensional aspect of our little hockey puck of soil, the soil can only move in one direction. So that's how we can find that change in height is equal to the change in volume. But first, what we need to know is the initial height of solid portion, because the solid portion is not changing in our sample. We're not removing any, or we're not adding any. So we find this using this equation. Height of solids is equal to the weight of the solids divided by the area of the sample times the specific gravity of the solids times the unit weight of water. So again, HS is the height of the solids, WS is the dry weight, of the sample. So, and then A is the cross-sectional area of our hockey puck soil sample. In other words, it's this top area right there. And then GS is specific gravity, which it was an experiment we did in Geotech 1. And then of course, W or gamma W is unit weight of water. And those two multiplied by each other is just so we can get that unit weight of the solid, right? That's what specific gravity is, unit weight of the solid divided by the unit weight of the water. Now, the important thing that I mentioned at the beginning is this right here. The weight, dry weight of the sample. This is found after the experiment. So that's why, like, you got to keep that in mind. We're collecting data, and I'll show you how we're collecting the data. But at the very end of it is when we take our sample out and we put it in the oven and we can find the dry unit or the dry weight. And then we use that data to populate all this equation, which then finds the original height of solid, which then makes all the other numbers make sense. So we have this Excel spreadsheet that we're just plugging in when we're collecting data, and then that initial input parameter we find at the very end, which is why it can be kind of dangerous, because if you drop the hockey puck and it spills everywhere, then you just lost all that week of data or sometimes a month of data. Okay, so once we find the height of the solid, knowing it's a three-phase diagram, we know that the height of the voids of our sample is equal to the initial height minus the height of the solid portion. Minus the height of the pod. There. So H is the initial so that would be just the initial height there of our sample. So what we can now find is the initial void ratio of the specimen. So the initial void ratio, this is often similar to the in situ void ratio. So this is the void ratio before we start any loading on our or any pressure being applied. So if we go back to, it's going to disappear, but if we go back to the plot here, where we have our void ratio versus the log of the pressure, and whenever we have the data that looks like this, blah, 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 something like that, our initial void ratio is going to technically be up here. It's not going to be shown on the plot. And this is a big area where I see a lot of mistakes. Our initial void ratio is not the initial, like the first point on here, because this first point has some type of loading applied to it, right? This is where our load is applied. And since this is a log scale, there's technically no 0 point here. So that's one of the things why you don't plot the initial void ratio for that. So, you know, homework and exam, when I give you the void ratio, I always see somebody still plot that initial void ratio point when you find it. That is not the case. It's used as like a top ceiling. So you would usually in the experiment, you would plot it or something and show it as a dashed line just to show that, okay, all of our data that we got is below that, which should make sense. Okay, so how we find this? Since we know void ratio, or the initial void ratio, so E is not, that is, the equation is the volume of voids divided by the volume of the solid portion. And since volume is just height times the area of our sample, then that area cancels out, and that's how math works. And you guys can calculate it by finding the height of the voids divided by the height of the solid. So that's what we found here in part 2 and here in part 1. So boom, now we can find the initial void ratio. So once we find the initial void ratio, all we need to do is find the change in void ratio at each incremental point, or sorry, at each loading increment, and then subtract it from the previous. So that's essentially what we're doing. So for the first incremental loading causing deformation, I'm going to call this change in height 1. Because remember, what is actually happening is we have, this hockey puck of a sample. And really what it was originally this high. But after the first increment, we have, this is our first H. This is going to be H1. And so that change is going to be change in height 1. And so that's from the dial gauge, we would measure that dial gauge, and then we know the initial height. So the change in the void ratio at this first point is delta H1, the thing that we measure, divided by HS, which is the initial height of solids. Because the height of solids is not changing through the entire experiment. We're not adding or removing any soil. So the theoretical height is not changing. So of course, we can calculate the new void ratio at this increment by taking the first one and then minusing, if that's a word, the second one like that. Now, this is an important thing because some people will show the data this value right here. Sometimes you might see this as cumulative deformation, and then sometimes you might see it as incremental deformation. So depending on how it's shown depends on what this value is right here. Because it's all the same for the first step. But for the second step, E2, normally it would be E1 minus the change from E1 to E2. But if it's cumulative, then we would still need to make sure that that is E not E0. Is that making sense? So if this value right here is incremental, meaning between 1 and 2, then we subtract it from 1. If it's cumulative, meaning from 0 to 2, then we subtract it from 0. So sometimes the data, and in textbooks and stuff, they'll throw those curveballs, and in the PE too, they might you're not going to be asked to do a whole analysis in the PE, but they might ask something similar to that. We always have to make sure that we're reading whatever this change in void ratio correctly, change in height correctly. So essentially that's how we would get all of this data. So again, this figure here is showing it good. The E naught is not plotted, but what we have is a pressure with a corresponding void ratio, and then another pressure with a corresponding void ratio, so on and so forth. And then that's what we are plotting here. And keep in mind too that these are always discrete points. So sometimes they'll actually look nice and smooth like that, but a lot of times you're interpolating this best fit line in between these data points because it's real data. So if you remember, there's 3 things that are important to read from the pressure plot, or whatever you want to call here. There is this slope here. And this is called C subscript C, which is called the compressibility index. There is this initial slope here. And that slope there is called the recompression index, or the swell index. That's shown by CR or CS. So essentially the same thing. And then there's the point at which these two curves, like the curve changes like behavior. And so that point, it's not always right in the dead center there. And we're going to talk about how we find it. But this point is on the x-axis only. It's a stress value. And this is called the pre-consolidation pressure. And this is shown by subscript C. Or sometimes it's just shown with a P subscript C, pre-consolidation pressure. So the two slopes, CC and CR or CS, these are slopes. So that's, you calculate it rise over run slope-wise. The pre-consolidation pressure is the point on the x-axis, which corresponds with that. And so let's talk about the way to calculate the pre-consolidation pressure, or estimate the pre-consolidation pressure, I should say. First thing you might notice, this was proposed and used in 1936 by Casagrande, Arthur Casagrande, and that's still what we use today. So literally, like, it's even like computer programs that estimate it, it still uses this technique today. It is a very old technique, but it's a standard technique, and that's the most important thing, because this number really doesn't mean that much as long as we're all still using the correct way to calculate it. That's kind of what an index is, So this is a very subjective way of calculating. And it's a little gnarly, so I'm going to go through it one step by step. I already had them wrote down there, but I'll show you how to calculate there. So the Casagrande method in 1936, what you first do is you visualize a point at which the curve has a minimum radius of curvature, which means it's the sharpest turn, right? So you're going to look at the curve. So first you have to fit the data with a like curved line like that, not like a straight point line, but you'll fit the data with a curved line. And we're just going to pick a point. Let me make sure I don't like have it come up automatically. Okay. So we're just going to call that, let's just say this point right here is that point. So I'm going to call this point A. So that's the point at which the curve is the sharpest, right? That's what the minimum radius of curvature means. So what we then do is Arthur Casagrande in his basement in 1936 drew a horizontal line here. And just for the sake of notation, AB. So that's going to be that horizontal line there. So that's going to be the horizontal line AB. So what you do now is draw a line AC. So this is step 3 that lies tangent to the curve at that point A. And of course, tangent to the curve is always a weird thing because you're just basically estimating how you think that point is tangent. But what that would look like, according to my best estimates, be something like this. Again, assuming this is an actual straight line. So you can do this with a ruler or Excel or PowerPoint or AutoCAD. It's a little bit better. So that's going to be the point A, and I'm just going to call that AC. That's this point right here. So then, just to make sure everybody in the alphabet is happy, we're going to draw a line and call this line AD, which is the bisector of the angle between B, A, and C. So that means what we do is we just take this angle and we're going to try to split it in half. And again, if you're using AutoCAD or something, you can actually measure that angle and then calculate it that way. So this is going to be AD. And the whole thing with that is that these angles are equal. That's what that's trying to say, which is a poor job, but that's what it did. So then what we do is we project a straight line of the portion here back all the way until they meet. So we're going to start down here, and let me choose a different color. Just go with black. So this straight line portion here, and pretend this is an actual straight line. We're going to have it just go infinitely back there, where it intersects with line AD, this point right here. That's what we're going to call F. And that point is the pre-consolidation pressure. So that is how we find the pre-consolidation pressure right there. Now, the important thing to remember with this is we are reading a semi-log scale. So that means that this value is not, 90 or something. It is 10, this is 20, 30, 40, 50, 60, so like 68 or something, somewhere between 60 and 70. So you could see how just, one shift this up a little bit or something, and you have a completely different way of doing it. So it's a sketchy test, but this is the standard method of how we find the pre-consolidation pressure, which is a major part of it. No internet back in the day, 1936. It was just a standard way. Like that's what you'll see a lot in geotech. A lot of tests don't make sense, but it's like this is a standard way of doing it, and everybody jumped on board, and now that's how everybody does it. So I don't know. There are other techniques out there, but this is still the most like standardized way of doing it. Yeah, a lot of geometry. And now like that's the good thing. Like now we can actually find the true point of max or minimum curvature and everything, So you can do it by hand, but you could also, if you want to be precise, then you can be pretty precise. But remember, the data that we're using to make this curve is also not precise. So it's kind of like a good experiment for what it is, because the input is not super high quality anyways. So all that to say, that is where we get the pre-consolidation pressure. And remember, this pre-consolidation pressure, you'll see this pop up a lot in the calculation, the estimates for how we actually get the settlement, the field settlement. That's why we can't be too accurate when it comes to estimating, we can't be too precise when it comes to estimating consolidation settlement. We always be or generalized numbers. All right, so the compression index, there are a lot of empirical relationships out there, and the FDOT actually has some of their own, and this is stuff where we're currently pursuing research to use machine learning actually to find all these variables, see how they relate to these compression indices, and then provide a model such that we can bypass doing this whole experiment. So some of the most common ones here, and they're all regionally based, but Skempton and Rothenwood, those are some of the equations there. You guys remember what this is here? LL. Liquid limit, yeah. So that's the little ding, 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 right? And then you have the plastic index too, which is even more sketchy. Void ratio and the other void ratios there. So these are just some of them that you might come across that are still used today in industry. But the important thing to remember with this is that, these are empirical relationships, which means data is used to create them. So data and statistics are used. So if we have an empirical model for glacier deposited marine clays in Norway, and that model works really good in Norway, do you think it'll work good here in Florida for organic soils? Yeah, probably not. So we have to always be aware of where these models are made and the data that was used to input to make those. So you can't just blindly take some and be like, oh, here's one I found from Google or ChatGPT. Like, let me just plug this in. Like that could be a pretty costly mistake when you're making some estimates that way. You don't need to memorize. these. Yeah, no, you don't really need to memorize anything in this class except sewage. No, that one. But yeah, no, all of this stuff is just reference. Like you'll see it again, like flat. All right, let's look at an example problem for a void ratio, like or a pressure plot. So let's find the initial void ratio, and then we're going to plot the E log curve. So the pressure, the consolidation curve. So initial void ratio, this is our E naught. And then this whole curve, that's going to be that cool thing that looks like this. So we are told that the diameter of the specimen is 2.5 inches. The initial height of the specimen is 0.78 inches. Specific gravity of the solid is 2.72. And then the dry mass of the soil is 75.91. Excuse me. So what we have is the pressure being applied incrementally. So going from 0 to 16,000 pounds per square foot. And then the dial is shown there. The dial is an incremental deformation. So as we are applying the load, the deformation right is at 0 when there's 0 pressure, and we're applying it incrementally here. Now, 16,000 pounds per square foot, that's a lot, right? But remember, what we're doing is we're applying this over a diameter of 2.5 inches. So that's how we can get away with only putting like a 20-pound weight on our sample, because that is being applied over a smaller area, so we can achieve those higher stresses. So although 16,000 pounds per square foot might be something that the soil is actually like in the field that the building is going to apply to, because we're normalizing for stress, we can apply it on a smaller area and achieve that, which is helpful. All right. So the first step that we do, just following that again, is we have to first, let's find the volume of the solid, so that VS. So the volume of the solid is the mass of the solid divided by the density of the solid. Right? You guys remember the whole, I think I drew this a bunch in geotech, the density triangle, D, M, V. So if you are trying to find the volume, we cover up the V, and then we have mass divided by density is just, or you just look at the units, or you just know it from common sense. Anyways, we need to find first the volume of the solid. So that's mass of the solid, which is 75, and then the density, which is from the specific gravity times the unit weight of water, or the density of water. Oops. So that's a W there. So since we are in grams here, density of water is just 1 gram per cubic centimeter. It's the beauty of non-US units. So that means that this is 75.98 grams divided by 2.72 grams per cubic centimeter. I don't know why they measure in grams, and everything else is in inches, but we'll convert that over a little bit. So, all right, so we can find the volume of solid. The volume of solid, calculating that out, is 27.91 cubic centimeters. So then we need to find the total volume. Because remember, why we're finding this is to find the volume of voids, to find that initial void ratio. So the volume of voids can either be done by the height or the volume. So let's find this volume or the total volume. So total volume, it's just the volume of the hockey puck, so a cylinder. So we're told the initial height is 0.78 inches. Initial diameter is 2.5 inches. So the total volume, just going to put V naught pi r squared times the height. And then doing that out, it is 3.829 inches cubed. And then since we have our VS in cubic centimeters, I'm just going to put it in cubic centimeters too. So which is 62.74 cubic centimeters. So now let's find the initial volume of voids, which is just the total volume minus the volume of solid. So that's 34.83 cubic centimeters. So 62.73 minus 27.91. So initial void ratio. This is volume of voids over the volume of solid. And so 38.83 divided by 27.91. I always just get choked up when I'm doing consolidation tests. And you could have done this in cubic inches, whatever, as long as the units cancel each other out, right? That's the beauty of ratios and math. Okay, so that gives us an initial void ratio of 1.248. And remember, this number is really important because this is what we're basing all of our curve off of, this initial point of 1.248. So now let's develop this E log P curve. So for each one of these loading increments, what we need to put is a void ratio associated with each one. Now, since we have this pressure of 0, we essentially already know that this void ratio for right here is 1.248. Even though we don't plot it, it's important to put that there, because remember, it's a semi-log plot, so there's no x-axis is equal to 0 kind of thing. Now, what we do see is that with this dial reading, the change in height for each one incrementally is going to be, you know, the change between that. So we can, as I said before, we can either start from void ratio and base all of our subtractions off of that, or we can work incrementally for that. So before that, to develop this, let's find the height of our solid, since that's what we are putting in our equation. You remember the change in void ratio between each one is the change in height divided by the initial height of our solid, because the height of the solid is not changing. So in order to find the height of the solid, this is our Vs divided by the area of our puck. Right? Volume of the solid is height times area, so we can find it conversely that way. So if we do that, calculating it using the area, then our height of our solid is 0.881 centimeters. So that's our pseudo height of our solid in our sample. And so the change in height here, even though it's in inches, you'd have to calculate it. So for this first one, change in height 1, this is going to be equal to 0.0158 inches, which is equal to 0.0401 centimeters. So it's a stupid example in the fact that they use the different units and stuff. But it's important to make sure you're switching around accordingly. So this is the initial change in height. So from that, we can find our initial void ratio, or sorry, first step void ratio from our initial change in height divided by our initial height of solids. Just making sure that the units cancel out. 0.0401 over 0.881 centimeters. So the 2 centimeters over centimeters. This change in void ratio is equal to 0.046. And it's a unitless number, right? Change in void ratio. So there's no units. The centimeters cancel out. So our new void ratio at load increment number 1, we call this E subscript 1. This is equal to E0, the initial, minus the change in the void ratio from 0 to 1. So what we see, again, the initial was 1.248, and then we subtract 0.0486. So our E1 is equal to 1.202. And then we do that for each step. So if you have an Excel spreadsheet, whatever, it populates it pretty quickly. That's the beauty of it. So I'm going to show on the next slide, we have the results from that. I don't want to go through the math like tediously and stuff. Hopefully it's clear for now. But you can see how we're calculating that. And the test should be, as we are increasing the load, we should see a decreasing void ratio, right? And so this is what we're plotting right here, y-axis. And then this is the x-axis. But the important thing to remember is when you're plotting this, we do not plot the 0. Because even if you put that data in there and then you double click on the x-axis and turn it into a log scale, a bunch of errors are going to pop up saying, oh, you can't do a 0 plot on there, and it'll mess it up. So remove that 0 plot on there and then plot the rest of this. And that is how we get the nice looking plot. So if it looks like this, then there's an issue. What it should look is like this because of the log scale here. So then in this case, the initial void ratio here, 1.248, right? It's not shown. There's not an actual data point, but we know that it's right here. This is our initial void ratio, somewhere magical, this magical line in heaven up there. And then from this is when then we would take this data and plot it with a curved line. And then we would do the whole thing from 1936 Casa Grande to calculate that way and everything. So just to show you, this is what some real data looks like from a consolidation report. This is for, I think I took this from the either Wekiva Parkway or the I-4 Ultimate project. So you can see what they did with the initial void ratio right here is shown in this report, 1.353. So that's like right here somewhere. And so you have this curve, and then for whatever reason, they decided to unload it in that early stage. Sometimes you do that to help like get rid of that initial compression stage. So you load it and then unload it and then try to reload it back again. And then you would have an unloading regime there. And so you can calculate the CC right here. And then the CR is just kind of estimated through here. So remember, when you're calculating the CC or the CR, any of these things, you have to make sure that you're using one, the rise over run equation that looks a little funky because it's a negative number in the top, E1 minus E2, but then also the log on the run portion because it's a semi-log plot. So it would look something like this, log 1. So you would pick 2 random points, or not random points, but you would find 2 points and then calculate that slope that way. So you can do this, and then it's plotted down here. It's shown that's CR, that's CC. Right here, this is our P sub C, which is the pre-consolidation pressure. You see the overburden is shown here. The overburden is just another way of saying the in situ effective stress. So this is our pre-consolidation pressure. Some of the other things, specific gravity, PILL, and then the saturation should be close to 100, and then the natural moisture content there, shown there too. So this is the DOT's kind of standardized way of showing consolidation test data. You can see down here, what else do you see? Elevation and depth. So that's at where the Shelby tube was collected from. The Shelby tube is 24 inches long, so they just push the whole Shelby tube through that 40 to 42 foot. And then the minus 200, you guys remember what that represents? Stack sheet.
Oh, see.
The sieves, yeah. So that's the percent passing the 200 sieve. So the smallest thing. So that is what is used to for the USCS, right? Remember?
It's a fatty clay.
Yep. Big old gray fat clay. This is a structure report. So this was for bridge boring. So they just were like, oh, we don't have to do that, I guess. So yeah, this is an example of the real thing. So let's just test. So this is the true data. So 40.42, right? So let's see. Looking back at those empirical relationships. This is, let's try skemptums and see what we get. So 0.09, and then this was the liquid limit minus 10%. So 0.009. The liquid limit is 98, so that would be 98 minus 10. If we do this, we get a CC value of 0.792. Now, the real CC value that we found from the experiment is 0.42. So that's pretty far off, right? That's not the best like accuracy. Roth and Wood, let's try that one. So CC, what they said was it's 0.5 times the specific gravity. And then that's the plastic index over 100. Yeah. So that would be 0.5 times 2.7 times 79 over 100. So if we do that math out, we get something worse, 1.70. So we're going the wrong direction. So far, these two tests or these two empirical methods are not lining up very good. All right. Rendon and Herrera. So they had a little bit more like heavy statistics based, not just a linear relationship there. They added some power functions there. So their equation that they're proposing is 1 plus the initial void ratio over specific gravity. And then, it's like a power function. So it's up to these crazy things here. Yes, 1.2. Yep. So this one, you have more input variables and it looks fancier. So this actually is 0.33. So we're getting a little bit better there. That's good, at least. And then the these people at Anderson's. Not even going to try to say that with the stuff he knows. This one was empirical as well. 1.56 plus, so just a higher order polynomial. And it was the overburden pressure. Wait, what was it? Oh no, the initial void ratio. And then minus 0.0058 times the liquid limit. So this is 0.48. So these aren't too bad. So these might be acceptable, right? I would not say, like, if you decided to use these and just open your textbook and find this, or Google and find a correlation, these most likely will not be applicable at all. So the big thing to remember with this is that a lot of these are developed either for normally consolidated clay or over consolidated clay. So normally consolidated or over consolidated clay. And so let's look down here and see. So remember, over consolidated means the current stress that the clay is exposed to is less than what it once was exposed to. And what it once was exposed to is the pre-consolidation pressure here. So this is the current. And this is the past max. So is this clay over consolidated or normally consolidated? Yeah, it's over consolidated because currently it only has 1.38 tons per square foot over it. But a long time ago, according to the pre-consolidation pressure that is based off of the 1936 technique of drawing a bunch of straight lines, the pre-consolidation pressure is 4.75, which means it used to have a higher stress above it. So that means that this is an over consolidated clay. So this would mean that we would need to use over consolidated fat clay empirical relationships and not just picking something out of the basket because it's the easiest math wise. That's a huge thing in geotechnical engineering. Regional models or regional empirical models or empirical relationships, because you can get really crazy results if you just pick an equation blindly. And that's why, if you're interested, I'll share this too. The DOT is looking into creating some of those equations, excuse me, specifically derived off of Florida soils. So this was actually a project I was involved with at UCF when I was in grad school. It was published in 2019. And we took a database of like 600 consolidation test reports and had to dig through it all and populate this. And then we would send the data over to one of the statistics professors. And he created these models that have a higher accuracy for Florida soils. And that's the whole goal of it, is like, okay, we can save the consultant time and money by, instead of running these month-long tests, we can estimate the CC and the CR values ahead of time to see if it's even worth putting or an embankment here or a surcharge here or a foundation here. So these are some equations. If you Google this report, you can see the values and the DOT. Their equations aren't pretty. You need an Excel spreadsheet or some type of thing, but use moisture content, liquid limit, and fine content as the variables there. Okay, so we're going to stop with this last slide. I'll get into the settlement in next class. So just as a summary, just to recap stuff, on Thursday, we'll finish it up. But clays have long-term settlement because the pore water pressure dissipates after loading. So it's a little balloon. If we put pressure on the balloon, it looks like a piece of bread, but whatever. And it's going to slowly leak out. The water's slowly going to leak out, and we're slowly going to have a change in volume. So this is change in volume over time, over a long time. The behavior of the clay is important and able to quantify that is the C sub C or the C sub R. So that's coefficient of compressibility coefficient or the recompression coefficient. And I want you to think these are very similar to like stiffness values or Young's modulus in clay, or stiffness or Young's modulus in metal. So just how that value is important to estimate the behavior in metal, these values are important to estimate the behavior in clay. And the benefit of this is we can do behavior of the clay in the lab to estimate the behavior of the clay in the field. And so if we can do this estimation, once we have these parameters, then we can estimate the consolidation settlement in the field before it actually happens, which is a really beneficial thing. So all we need to do is take this little tiny sample and then apply load to it over time to produce CR and CC. And then from that, we can estimate field settlement. So it's a time extensive test, but it's way better than doing the real thing and building a $1 million roadway and then having that settle. All right, so we'll talk about the settlement from 1D primary consolidation next class. Hopefully the computer is my friend next class. So I'll see you guys then.